All right, last time we started section 3.3, which is multiplication and division of whole numbers. We talked about, as we were ending class, the three models for multiplication, and you guys gave me examples that you created. So repeated addition was this idea that we add something multiple times together, and so array, which is still multiplication, has sort of this visual imagery of something that is in rows and columns, but they're whole objects that we count as whole objects, whereas area measures some sort of spacing of things, and so we think about gardens and dog houses and things like that when we looked at area. So where we're going to start today is the properties of multiplication. These are very similar, and some of them almost identical to the properties when we did addition. And we've got some new ones that we have as well on our multiplication properties. So the first one is closure. Closure is the one that makes everyone feel just a little bit uneasy. But closure, again, is the idea that if I take two numbers in a specific set, and right now my specific set is whole numbers, and I multiply two whole numbers together, I get another whole number. Okay? We did it with addition. You add two whole numbers together, you get a whole number. So now we're doing multiplication. You multiply two whole numbers, you get a whole number. And again, we can look at multiplication or look at closure with multiplication with things that aren't just whole numbers, right? So we can talk about even numbers. If you multiply even numbers together, do you get even numbers? You do. What about if you multiply odd numbers together? Do you get odd numbers? You do, always, actually, yeah. So while even numbers were closed with addition, odd numbers were not closed with addition. Remember that? Odd number plus odd number, not odd. But they actually are closed with multiplication. Odd number times odd number, another odd number. So closure, again, is the idea of whatever set we're talking about, being able to take it, operate two numbers in that set together, and get another number in that set. The community property says that the order of multiplication in this case also does not matter. So 5 times 3 is 3 times 5. And we talked about this with addition. This is one of those really helpful facts for children when they're learning their multiplication tables, right? So at some point when we get to the 7s or the 8s, there's fewer new multiplication facts to memorize because you've memorized a lot of them already when you did 3 times 7. Right, and 4 times 7. You already knew those multiplication tables of 7s by the time you get there. So that's the commutative property. Operations can be switched around. The associative property says that the order, the grouping of them, we'll say it that way, the grouping of our multiplications when I have three terms or more doesn't matter either. So if I have A times B, and then we multiply that times C, I could multiply B and C first, and then multiply A second. So grouping symbols, how we're associating the multiplication steps together is not unique. It doesn't matter. We won't get the same answer either way. We had an additive identity property. What was the additive identity element? What number? It was 0, right? 0 plus anything is 0. I didn't say that right. 0 plus anything is the anything that we already have, okay? So that was the additive identity property. Multiplicative identity property, a different one, so you can't just say identity because there's two different identities, is the number 1. That's the element. So the number 1 can be multiplied by any number, and it will leave that other number unchanged. So 7 times 1 is 7, and 1 times 7 is 7. And just like with the additive identity, it has to work on either side, which is exactly why subtraction failed. So 5 minus 0 was good, but 0 minus 5 was not. Same thing's true for multiplication and division. We have this multiplication identity, times 1, but we're going to see the division identity fall apart a little bit in one direction. Oh, one other place that we see let me go back to it, that we see the identity used that we don't often think about is when we're actually trying to either simplify or combine fractions together. So you guys are very familiar with the idea of sort of multiplying the top and bottom of a fraction by the number 2, right? So that you can change the value in the denominator. Maybe you're trying to combine fractions together or something like that. That's what you're doing, is you're multiplying by the number 1. So the reason I can multiply by 2 over 2 is because 2 over 2 is 1. It doesn't actually change the value. So that's the multiplicative identity property at play when you're using fractions very clearly. All right, the zero property. The zero property for multiplication simply says that when I multiply by 0, I get 0. And again, the order of the multiplication doesn't make any difference because multiplication is commutative. New property, well, the zero property is a new property, but so is the distributive property. So the distributive property is a property that combines operations. So it combines multiplication with addition or multiplication with subtraction. And it tells you that when you multiply something that is added or subtracted together, you could multiply each of the individual add-ins together to the numbers, so AB and AC here, and then you could add or subtract whichever way you had it, the result. So the distributive property works over addition or over subtraction. All right, so just like when we did the adding properties, the addition properties, we're going to do the same type of question here with multiplication properties. There are 6 statements here, and I'd like for you to go down the list and try to identify which property is being used. Once you're done, find somebody near you who is also completed, or wait for them to complete, and compare your list and see if you have the same property listed for each of the 6 examples. Yeah, so if you've got an identity property, you're going to say additive identity or multiplicative identity. So you just need to identify which of the two you're using. Mm-hmm. Okay, has everyone had a chance to check in with someone on at least a few of them? Yeah? Okay, let's go through them and see what kind of properties you guys come up with. Which property do you see happening on part A? Yeah, it's the zero property. How about on part B? That is commutative. How about on part C? Good, that one is associative, and you have to look carefully at those two. They kind of feel like they look the same, but they are doing different things in B and C. What about D? Yeah, that's the multiplicative. Identity, I'll put ID. How about E? Yeah, E is distributive. And how about F? It's a weird looking one. So Michaela said it's distributive, and she is correct. So here's the way to think about that one, because it does look weird. They're taking the 1 plus 2 in parentheses, and they're distributing that whole quantity that's 1 plus 2 to the 3, and then the 1 plus 2 to the 4, right? So that's the distributive property, even if it looks a little funky. All right. So this is where I normally would have stopped on multiplication, but we just couldn't quite get there last class period, okay? So we're going to shift gears now into division and talk about division. Just like when we started with multiplication, addition, and subtraction, we're going to define what it means. So to start with, we have whole numbers, A and B, and the value of B cannot be negative for the definition to make sense. So if we have A divided by B, this is going to equal C, if and only if C is the unique whole number such that B times C is equal to A. A is called the dividend, B is called the divisor, and C is called the quotient. And kind of like when we talked about this with subtraction in particular, it makes sense to define division in terms of multiplication. Just like with subtraction, it made sense to define it in terms of addition. So if a child has already learned their multiplication facts, they should be able to switch into doing division pretty smoothly. And so you will find out very quickly which of your kiddos really don't know their multiplication facts when you get to division, which is exactly what happened with our daughter. That was lots of fun. We dealt with that this semester. So it looks something like this. The reason that 6 divided by 2, that we know it equals 3, is because in the same fact family, we know that 2 times 3 is equal to 6. And this is the multiplication fact that we should know before we ever arrive at division. Does that make sense? So that's how this definition is created. It's created on knowing multiplication first. And we do have the problem with not letting the denominator or the second value equal 0. And hopefully you can see why that's a problem. If I were to try to do this and it equaled something, I'd have to be able to take 0 and multiply it by that something and get back 6. And that's not possible, right? And that's exactly why this idea of division doesn't work and why you can't divide by 0 from a definition standpoint. All right. So there are several models for division, but some of the models for division are actually the same. The problems are simply worded a little bit differently. So in particular, the first two models for division are actually not even identified as different types in your book. I want to identify them as separate for you because when you get to proportional and statistical reasoning, one of them works once you move into the rational number system. The other one doesn't. And so grouping them together feels a little awkward to me. So here's an example. We have Junie has 24 rocks, and she wants to give them to 6 of her friends. How many rocks will each friend get? So when we're looking at the set partition model, we're wanting to partition the 24 into 6 groups. So you sort of have this idea that we've got group 1 because we have friend 1, we have group 2 for friend 2, group 3 for friend 3, 4, 5, and 6. So I've got these sort of like cups sitting out, and I'm going to divide my 24 rocks into the even 6 cups or to the even 6 friends or whatever. So that's the idea of this model, is that I put them in groups and I have 6 groups. Okay, so if I'm working with my rocks in this case, right, I can actually draw these in. It's an interesting color of a rock. Let's try that one instead. So what you would physically probably do if you were Junie is that you'd go through and you'd give them each a rock, right? And you'd say, hey, look, I still got a bunch of rocks. And you'd go and you'd give them more rocks. And you'd evenly divide them up until you got rid of all 24 of them. And the answer then would be the number of rocks that's in each rectangle that I've given to each friend. So my answer would be that each friend gets how many rocks? 4 rocks. So in this model, the idea is that I know the number of groups that I'm separating things into. So in order for this model to make sense, I have to be dividing by something that's actually a whole number. So this model doesn't make sense for fractions. I can't divide something into half of a group. Are you with me? So this model does not extend very well into the rational number system because I can't divide by fractions and talk about making groups of fractional amounts. That's weird. Okay? So making a fractional number of groups, I should say. So the next model actually lends itself better to that idea. But if you read it, you're going to feel like in the same thing. Well, it is. It's still division, of course. So Junie has 24 rocks. Here, she bags them together in groups of 6. If she gives one bag to each friend, how many friends will receive a bag of rocks? So now we've got our bags of rocks. And it says that in a bag of rocks, she's going to put 6 rocks, right? So literally what she's going to do is she's going to take her bag and she's going to put 6 of them there. And once she's done, she can seal the bag up. And she's still got rocks in her, in her hand. And so she says, okay, well, I can give some more away. And so now I'm going to put, 6 more rocks in a bag. And then I'm going to do another bag until I end up getting rid of all my rocks. And the answer to this one is asked, the question being asked is how many friends get rocks? And the answer would be 4 friends. So what I know in this model is I actually know, like over here I wrote down where I know the number of groups. Here what I know is I know the size of the groups. Right? I know when the group is full once I got to 6. And I can extend this one into rational numbers pretty well. So if you think about taking a bunch of cookies and you want to put them in groups of size 1/2, well, it just means that you need half a cookie in each group. I can make a group of size 1/2. Okay, not 1/2 peoples, obviously, but 1/2 of a cookie we could do. Whereas I can't make a group of cookies where the group has size 1/2. Right? The individual number of groups is 1/2, I should say it that way. I can do a size of 1/2 group, but I can't do a number of 1/2 groups. Anyway, all right, so this is a model. These are both considered the partition models, okay? There's 2 more. There's missing factor, and then our last one is a number line model. Sorry, not number line, repeated subtraction model. So the missing factor model, here's your idea. It says Junie has 24 rocks. She wants to give them to 6 of her friends. How many friends will each rock get? This one actually looks more equation-like. What's wrong?
You said how many friends will each rock get?
Oh, well, there you go. Thanks. Appreciate it. I just keep talking. I don't know what I'm saying. It looks a lot like the equation we set up. So we have 24 divided by something. And it says we want to give them to 6 friends. So there is a missing factor in my equation that I'm setting up. And so I'm thinking of it more from an equation standpoint when I'm looking at missing factor. And so I have a 4 here. All right. Repeated subtraction is going to feel like what I did over here on this problem when I put the rock in each person's bucket and then I said, oh, look, I still have more rocks and I'm going to add one more to each bucket. So repeated subtraction actually has that same feel to it. 24 rocks, 6 friends, and so forth. But here's the way repeated subtraction works in small quantities. I'm going to show you how to do it in bigger quantities when we get to section 3.5. So when the numbers get bigger, it looks a little bit different. But the idea for repeated subtraction is I have 24 of the original rocks, and I want to divvy them up equally, of course. And so once I have given each of the 6 friends a rock, I have 6 fewer rocks to give away. So if I have 24 minus 16, what do I get? 18. I think I said minus 16. I meant to say minus 6. 24 minus 6 is 18. And if I subtract 6 again, because I've given each of my 6 friends one more rock, I have 12. And I'm running out of space, so when I subtract 6 again, I get 6. And then if I subtract 6 again, I get 0. So either I get 0 or I simply get fewer than the number of friends, and then I'm done. So how do I figure out my answer? Well, the question is, how many times did I subtract 6? So over here I subtracted 6. Wow, that wasn't what I meant to do. Let's use this. I subtracted 6 1, 2, 3, 4 times. So since I subtracted 6 4 times, in essence I gave each of my friends a rock 4 times, which means how many rocks did they end up getting? 4 rocks, right? And I'm not trying to trick you, I promise. So there are 4 rocks here at the end because I did it 4 different times. When the numbers get bigger, this feels different because I can't subtract. If you had 552 rocks, you're not going to want to subtract 6 that many times, right? So there's an alteration for how you deal with that. We'll get there later. So a little bit of a note, it's in your notes as well. It says 3 of the 4 models above do not really represent different types of word problems like we did with subtraction, for example, but they represent different ways of solving the same word problem. So how are we dividing things up? Are we doing it with an equation standpoint, or are we doing it with a repeated subtraction standpoint, that kind of stuff? So what I would normally do is I would normally have you guys create the problems, but I think what I'd like to do is go ahead and move on past this because these problems are very similar. When you create them, you really don't create like 4 problems. And that way we'll have time to do the group work at the end and it won't become homework. Does that sound okay to you guys? Okay. So let's take a look at the properties for whole number division. So the question becomes, if we have all these properties, and there were 6 of them for whole number multiplication, which of those whole number multiplication properties actually apply to division? And again, I did it on a video. I didn't do it in class with you, but I did this for subtraction too. We had our whole number properties for addition, and the question was which ones hold for subtraction. So let's start with the closure property. So again, closure means if I take any 2 elements of the whole numbers in this case, because I'm working with whole numbers, and I operate on them with, in this case, division, do I always get a whole number? Can you give me an example? I'm seeing several people shake their heads no. What's the problem? Can you give me an example of one that wouldn't work?
Would this be like 6 divided by 0?
No.
Is that what you're talking about?
No, although 0 itself causes a problem. Can you divide by another number besides 0 for me?
What about 5 divided by 2?
That'll work. Okay. So, oops, I don't want to write it as a fraction. 5 divided by 2. Those are both whole numbers that don't defy the sort of the definition, which is kind of what you were wanting to sort of break for me, Michaela. But these actually work with the definition. I can do 5 divided by 2. The problem is that 5 divided by 2 is not a whole number, right? This is equal to 2.5, as you're well aware, or a fractional version, or a 2 1/2 from a mixed number. And this is not an element of the whole numbers, right? Just not. And plenty of the numbers do that with the whole numbers, where when I divide them, I don't get whole numbers back. So the whole numbers are not closed with respect to division. How about commutative? Now, that's a no. So even if I find one that actually works in one direction, like 6 divided by 2 is 3, right? What happens when I try to switch the order? 2 divided by 6. Yeah, it's 1/3, which is not 3, right? The order of multiplication doesn't matter, but the order of division matters. Things get a little trickier with the associative property. But if you're just guessing, do you think it's going to work? Probably not, right? It doesn't, so let me show you again an example. So let's say we do 12 divided by 4 and then divided by 2. So if I do 12 divided by 4 divided by 2, I would 12 divided by 4 first, which is 3. And it's not a whole number, but let me show you what happens when I do it the other direction. If I do 12 divided by 4 divided by 2, what do I get? Starting with the 4 divided by 2. Yeah, I would actually get 12 divided by 2 on this one at the end, which is 6. And that's not what I'm getting here, right? So the order of association, how I group my elements together, matters, just like the order in terms of commutativity mattered. I already alluded to this one earlier, the identity property as not working. And the reason that it fails to work is because it only works sort of in one direction. So if there's an identity, it would have to be a number that divides things and leaves them unchanged, like the number 1. Right? 5 divided by 1 is 5. And that sort of looks like, yay, viable candidate. But if I switch the order, it fails, right? You got to be able to do it in both directions, and it simply isn't possible to do this in both directions. What about the 0 property? It works in one direction. Kristen's telling me, yeah, absolutely. And it does in one direction, right? Like 0 divided by 3. That one's 0, so that's good. But what happens if I try to do it the other direction? Yeah, good job. It's undefined. This is exactly the place where we started our discussion of division. Can't divide by 0. When I try to define the definition, when I define this in terms of multiplication, there is no number that multiplies by 0 to give me back 3. So this is not the same quantity, so these are not equal, right? Distributive property, kind of like with associative property, is a little bit funny to check for, so I just want to give you an example. It doesn't work either. Surprise, surprise at this point. But let's say I had 20 plus 10, and then divide by 5. So if I did 20 divided by 5 plus 10 divided by 5, I know I'm writing them in fractional form, but I think you guys can handle it. What's 20 divided by 5? 4. And 10 divided by 5? 2, and that would give me 6. What if I did it right here? What's 20 plus 10? 30. And 30 divided by 5 is 6. So in this direction, I end up with an equal statement, right? But much like what happened with the identity element and with the 0 property, it doesn't work if I go the other direction. For example, if I did 20 divided by 5, or sorry, 10 plus 5 is what I have written down, so we'll do that one, 10 plus 5. Well, if I try 20 divided by 10 and 20 divided by 5, so what's 20 divided by 10? 2, and 20 divided by 5? 4, which results in 6, just like the last part. But let's try what happens if I do it directly, right? So this is what happened when I went this direct route. So we're going to do the same thing on this one. So if I try this, I would do 20 divided by, and what's 10 plus 5? 15. And 20 divided by 15, well, whatever it is, it's certainly not 6, right? I'm not going to get the same result. So this is not going to hold either. So it's like all sad. I mean, everything worked beautifully for multiplication, just like it did for addition. But subtraction and division just fall apart. They are really, truly different operations when it comes to closure and identity elements and so forth. All right, I have one more example, and then we'll get to some group work today. We have JJ, and JJ claims that the following is true by the distributive law, where A and B are whole numbers. So his property that he believes is true is that 3 times A times B is equal to 3 times A times 3 times B. And the question is, how would you help him? So whenever there's that question, that's how you would help them. You better be using words, right? It's like an explain question from your test, right? Explain, use words. But there's often more than one explanation that are perfectly viable and helpful, or maybe not, depending on JJ's perspective, right? So somebody tell me some ideas that you have when you would be talking to JJ. What might you try with him? Do you want to talk, Michaela?
So I think
Okay.
first to explain that, like, you would take 3 and then times it by just A and B separately and show him, like, you know how you do the arrows where you like 3 times A
Okay.
and then you would do like times 3
Okay.
times B. You wouldn't do
Okay.
like 3 times A times 3 times B because then you'd have to distribute it all. Does that make sense?
It makes sense, but why are you going to tell him that there's a problem with that? Because, I mean, like, I just drew the arrows, right? So what's wrong with what I did?
Isn't by definition it's supposed to be, like in the parentheses, it'd be A plus B?
Ah, okay.
Because
So,
right now he's multiplying both values together after you distribute it.
okay, so one thing that we might remind JJ is that distribution combines operations. Right? So it combines multiplication with either addition or subtraction. And he doesn't have two operations here, right? His operations are multiplication and multiplication. Okay? So let me play, I was about to say devil's advocate. We'll say JJ's advocate. Let me play JJ's advocate and say, okay, but why? Why, Miss Bowers? Why doesn't it work?
Because that's the definition.
It's a definition. It's true. But I have a feeling that JJ is kind of like a little, less than happy with because it's a definition. How could we help him to see it not work?
Counterexample.
Yeah. So it's a good idea when something's not going to work and you know by a definition to actually show it not work. Usually there's multiple places where you can do that or multiple ways in which you could do that. And so an example might be really good. So for instance, let's say that you had some numbers in for A and B, and it doesn't really matter what they are. So somebody pick me something. Don't use 0. That's not going to be helpful at all. 4 and 7. Okay. Of course, y'all are going to get big numbers. Really? Can I just do like 2? All right. All right. Let's do 4 and 2. So if you're using sort of the left-hand side of this, what it's saying you would do is that you would multiply the 4 and the 2 first. So what is 4 times 2? 8. And then what would be 3 times 8? 24, right? Okay. So this is what would happen on the left-hand side of what he's proposing to do. And then according to the right-hand side, what we're trying to sort of test and show him doesn't work is that if I multiply 3 times 4 and I multiply 3 times 2, I'm not going to end up getting 24. So what is 3 times 4? 12. And what is 3 times 2? 6. And what is 12 times 6? That's 72. And so we can see with an example that these do not equal one another. It is actually quite useful to show them how they're related, though, too. if you were to take 24 and multiply it by 3, what would you get? 72. And the reason is because when you do this, you've actually introduced an extra factor of 3 that shouldn't be there. So that's why you can see that that's how the numbers are not equaling each other, because of that extra 3, as an example here as well. So this would be another way of sort of showing it on specific example form. All right, so what we're going to do next is we're going to do group work from this section, and then this homework assignment will be due on Monday.